In this video, we're going to do one more example where we are going to try to find an optimal solution. So here we have 4 feet of wire is being used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? What if we wanted to enclose the minimum total area? So here we're going to have a square, and we have a circle. So let's call the dimensions of the square x by x by x by x. This circle, if it has radius r, then the circumference of that circle is 2 pi r. We know we have 4 feet of wire, so 4x plus 2 pi r should be equal to 4. And what are we trying to optimize? Well, we want to optimize the total area. And so that area is going to be x squared plus pi r squared. And so we have the area of the square plus the area of the circle. Now, if we're going to find our optimal solution here, we should rewrite this function that we are trying to optimize. We want to rewrite that in terms of a single independent variable. So up here on our secondary equation, let's solve this for x. So if we were to solve that for x, we would have x is 4 minus 2 pi r over 4, which is 1 minus pi r over 2. And actually, let me write this as pi halves r So this area that we want to optimize is 1 plus 1 minus pi over 2 r squared plus pi r squared. Excellent. If we were to FOIL this out so we can combine some like terms, foiling that out, we will have 1 minus pi r plus pi squared over 4 r squared plus pi r squared. And if we were to take our derivative, our derivative is going to be negative pi plus pi squared over 2r plus 2 pi r. What do we do with this derivative? So what's our goal? We are trying to find the best solution. So we took the derivative so that we can find a critical number. When we find that critical number, we are going to be able to do a sign chart to determine if it's increasing to the left of it or decreasing, and then similarly to the right of those critical numbers. So we want to set it equal to 0 to find any critical numbers. Here, we can add that pi to the other side, divide by that remaining mess. So that is our value of r. We could clean that up a little bit. If we were to multiply the top and bottom by 2 over pi, then on top we would be left with 2. On bottom we would have pi plus 4. So that radius is 2 over pi plus 4. Excellent. If that is our radius, then what is our value of x? Right. So our value of x is 1 minus pi over 2 times that radius. So that came from right up here. And so our value of x is, if we were to clean that up, we get 4 over pi plus 4. So the 2's here cancel, and then if you were to get a common denominator, you would have pi plus 4 as a common denominator between the 1, so multiply this by pi plus 4 over pi plus 4, minus the pi, leaves you with just 4 on top, and your pi plus 4 in that denominator. So as a radius, we have a value that is about 0.28 feet. And our x value, the lengths aside for the square, are approximately 0.56 feet. Now, is that a maximum or a minimum area? Right. Well, we need to think about what is a feasible area. So we're going to do a sign chart for our total area, A, and we're doing a sign chart for the derivative of that. We are using just the values of r here initially, and so what feasible values of r? Well, we could have 0, right, so no circle at all of that's used in the square, so 0 up to 2 over pi plus 4, or 2 over pi plus 4 up to, if it's all used for the circle, then 2 pi r, the circumference of the circle, would be all 4 feet. So our radius would be 2 over pi. So those are the values that will make sense. We observe on this when we do our sign chart. If you choose something between 0 and 2 over pi plus 4, you'll get a negative output, and then you get a positive output. So at 2 over pi plus 4, we are at a minimum. So we have a minimum area when x is 2 over pi plus 4, which is approximately, not x, r is 2 over pi plus 4, which is approximately 0.28 feet, and x is approximately 0.56 feet. So that's our minimum area. We are also asked to find the maximum area. So where does that maximum area occur? Well, we previously saw that if you have a closed interval, then your maximum will occur at either critical value or at one of the endpoints. So here we really have a closed interval from 0 to 2 over pi. Those are the only values that make sense. So we need to check and see what's happening at the endpoints. So what happens when all of the area all of the wire is used for a square, and then what happens when all of that wire is used for the circle. So if it's all for the square, when r is 0, then our radius, not radius, our area, is going to be all in the square. So if r is 0, then x is going to be 1, and that total area is 1. When r is 2 over pi, so it's all used in the circle. If that's 2 over pi, then your value of x is going to be 0. Right? So this would become 1, and 1 minus 1 is 0. So this part goes away, and we have pi times 2 over pi squared. Pi times 2 over pi squared is 4 over pi, which is a little bit more than 1, so like 1.27. So this is the maximum area. So use all the wire on the circle to get a maximum area. And nothing on the square. Perfect. That is optimization, and that is it for Chapter 3. We will see you in our next videos when we look at trying to reverse everything that we've talked about. So if we start with a derivative, how do we go backwards and try to recover the function that it came from? So we will see you in our next videos. Have a good day.